Yesterday we saw how position and velocity versus time graphs can help us make calculations. Today we're going to develop some formulas so that we don't have to draw graphs every single time. In order to develop these formulas, we need to be very general. Let's just say an object starts at a specific speed and it accelerates up to a final speed in some amount of time, which we'll call t. To start, let's draw a velocity versus time graph. Ta-da! And we'll say this is an initial velocity of v naught, and this is a final velocity of vf. This is 0 seconds, and this is t seconds. So let's begin by looking at the slope of the line. That would help us calculate the average acceleration. Remember that slope is the change in y over the change in x. So in this case, the change in y would be the final velocity minus the initial velocity. And the change in x is simply t, because t minus 0 is t. And we were told that slope of a velocity versus time graph gives us acceleration. So this here could be a formula, but I'd like to rearrange it a little bit, make it a little bit easier to use. In kinematics, one of the most common things we need to find is the final velocity. It's usually not told to us. So let's solve this equation for Vf. To do that, multiply both sides by time. That gives us Vf minus V naught equals AT. And then if we add V naught to both sides, we get that Vf is equal to V naught plus AT. This here is the first of 4 major kinematics formulas that we're going to use throughout this chapter, 3 of which we're going to derive today. Now let's find the distance that this object traveled in this amount of time. And remember that that's the area that's underneath this curve. If I draw this line down, let's break it into a rectangle and a triangle, as we've done a couple times before, and find the area of each of these. The rectangle is V naught tall and time wide. And so multiplying those together is simple enough for the area there. This triangle is Vf minus V naught tall and time wide. Remember, the area of the triangle is 1/2 base times height. And so the area of this triangle would be 1/2 times Vf minus V naught times the width, time. If we put that all together, we get that distance traveled is V naught times time, that's the rectangle, plus the triangle, which is 1/2 Vf minus V naught times its width of time. And here's a formula we could use, but it's pretty ugly. Let's see if we can clean it up a little bit. If we distribute first, we get V naught t plus 1/2 of Vf minus 1/2 of V naught t. Here we've got 1 V naught t minus 1/2 of a V naught t gives us 1/2 of a V naught t plus 1/2 of a Vf t. And if we factor out the 1/2 and the t, this gives us 1/2 V naught plus Vf t. You might wonder why I chose to write it that way, but this half of 2 things added together, that's how you find an average. This here is average velocity times time. It's a very useful formula that the distance traveled is simply the average velocity times time. And that's usable anytime we know the initial and final speeds. Unfortunately, we don't always know the initial and final velocities. Sometimes we know the acceleration, but we haven't been told the final velocity. Let's go back and we'll make a small little substitution which will give us a completely different looking formula. If we go back to this starting point, I remember when we derived the formula for acceleration, at some point we had Vf minus V naught equaled AT. Let's make a quick substitution then. Instead of 1/2 Vf minus V naught, let's replace that with AT. And there's still this t at the end. That gives us a formula that the distance traveled is V naught t plus 1/2 the acceleration times time squared. This equation is useful because we can calculate the distance something travels, and all we need to know are the initial settings, the initial speed and the acceleration, and how much time it's traveling. So let's summarize what we found. First of all, there are some formulas that we've already learned from definition. The average velocity is simply the change in position over time. The average acceleration is simply the change in velocity divided by the amount of time. And then today we've derived several other formulas. The first we derived was that the final velocity is equal to the initial velocity plus acceleration times time. Then we derived a formula based on average velocity. Before, we had derived that distance is equal to average velocity times time. Here I made a little bit of a substitution and put in the final position and the initial position because we want to be able to, at times, start from a position that isn't 0, and this will allow us to do that. Here's our third formula that we derived. Remember, we had derived that distance was equal to initial speed times time plus 1/2 the acceleration times time squared. Again, I made the same little substitution to allow us to use an initial position if need be. And we have here a formula that calculates a position of an object given its starting position, starting velocity, and its acceleration. This one here is probably the most useful of all the different kinematics formulas we've been given. And at times, this one proves to be useful as well. I'm going to give you one more formula for free. Notice that each of these formulas has time in it. Quite often, you're given a problem and you aren't told how much time it takes. You could calculate how much time it takes and then use one of these formulas. However, this formula allows you to calculate things without knowing the time. It looks a little scary because of all the squareds, but this formula, the final velocity squared is equal to the initial velocity squared plus 2 times your acceleration times your total distance. Or if you need to, you can break that into final and initial positions. I will not take the time to derive this particular formula for you, but you could find it pretty quickly by taking any of these equations and solving it for t, and then substituting it into a different one. What I would highly suggest you do is that you take each of these formulas and that you write it on a note card. Perhaps your note card would look something like this.